Hi everyone and welcome back to Astronomy 10. Today we are going to continue our discussion with stars and stellar evolution by talking about the death of stars. So let's first talk about low mass stars. So a low mass star is considered to be a size that is similar to the sun, and as the star goes through its evolution, it forms into a red giant, as we saw in our last lectures, and then to a planetary nebula. And we want to know what happens after that planetary nebula stage, or what is left behind. And I did briefly mention it, that there will be some core that is left behind. And we're going to first consider cores that are less than 1.4 times the mass of the sun. So relatively close to the mass of the sun. And stars that have masses less or equal to or less than 8 times the mass of the sun can lose enough mass to become a white dwarf. And this is what we see um, happening to these stars that are similar in size to the sun or mass of the sun. And here on the right hand side, we can see an HR diagram, right? We've got our luminosity and our temperatures down here. It's just a little bit extended with the temperatures because, let me get out a laser pointer here, because this star will evolve past and get so hot it's not on the typical scale that we see. So I believe the surface temperature maximum of the HR diagram that we saw last week ended at about 30,000 Kelvin, so it'd be like somewhere around here, but it has to extend past that because the surface temperature of the star will be hotter, much hotter than 30,000 Kelvin at some point during its evolution. So, this is an idea of a star that is more massive than the sun. Sun would be somewhere around here, I would say, lying on that main sequence. And it evolves through to the white dwarfs that we'll see here. So let's look at the cause of this. So what happens is the core that is left behind, the after the planetary nebula goes kind of goes away or continues to move away, the core will contract or um, kind of collapse into itself until it becomes degenerate. Now, what does that degeneracy mean? This means that the electrons will push together as close as they possibly can. They'll kind of, you can think of it as a crowd, and the people are kind of mushing themselves closer and closer together um, until it uh, kind of becomes impossible to get closer, since people, just like people, these electrons can't be in the same place at the same time. They do take up some space. So this limit is called the quantum mechanical limits, or the Pauli exclusion principle, where we can't get any closer. Basically, these electrons cannot get any closer. And the degenerate electron pressure supports the core against gravity. Now, do I have a picture of this? I do. This is just on the wrong slide, but we have the pressure of these degenerate electrons pushing outward against the star, perhaps, and the gravity of itself is pulling in. So we have an outward pressure and an inward pull of gravity. And this is what is going to keep the object from collapsing against itself. or into itself, because we have this pressure outward and gravity inward, and so it will remain stable, and we call this a white dwarf. And you can notice from this image here, a white dwarf is similar in size to the Earth. It's very comparable versus the sun. This is just, one little tiny piece of the sun, comparing the sizes. And like I said, it'll become stable. The density of the white dwarf, it is so dense. It is about 1,000,000 times the density of water. And remember that density has to do with how much stuff is within some sort of volume, right? How much stuff can we fit into maybe, I don't know, a cup, right? A cup of something. So this material is so dense, there's so much stuff in that cup, um, and we can compare that to our day-to-day lives, like a cup of liquid or whatever it may be. Comparing the two, it's almost as if there is so much empty space in that cup. Even though it's filled with liquid, that liquid is not dense, right? It's not very dense. So most of what we have is actually empty space. And this core of material that was left from the star is very dense, like I said, about 1,000,000 times the density of water. Okay, so here is another diagram similar to the HR diagram, and this is going to be the sun's path to a white dwarf. So it's on the main sequence now. It will eventually puff up, like we said, and become a red giant. Then it'll start to, it'll engulf the closest planets and become a planetary nebula. And then in the middle will eventually become a white dwarf. So it'll be um, collapsing or condensing itself so much that it will become a white dwarf. So again, these electrons will become very, very close together, but they can't be in the same place at the same time. And so this is where we get this degeneracy. Okay. So there is a limit to this. So the electron degeneracy can support a core up to 1.4 times the mass of the sun. So if the mass of the object is larger than this, it won't become this white dwarf. So because of the pressures, the white dwarfs with larger masses become smaller in size, and more massive cores become unstable and will continue to collapse. So this is that, it's called Chandrasekhar limit. Um, this limit of 1.4 times the mass of the sun, this is the limit of the white dwarf size. Okay, so we can detect white dwarfs, and we have, first of all, by visual detections, and also looking at binary systems. So there are binary systems out there where there's two stars rotating together, so, or orbiting each other, I should say, and one of them may be a white dwarf. And in these binary star systems, we can have transfer of matter or transfer of mass from the from one of the stars, or an ordinary star, to a white dwarf through an accretion disk. Now let me show you what that would look like. Let me get my pen out real quick. Give me a second. Sorry. Okay. So in this case, we'd have, say, a normal star, and it's rotating and orbiting, um, and we'll have some sort of accretion disk onto a white, come on, onto a white dwarf, and it will accrete material onto that white dwarf. So this is, say, an ordinary star, and in the middle there is a white dwarf. So we can observe this phenomenon happening. Now, these very specific type of binary system is called a cataclysmic variable, and I actually studied a type of these, and if you're interested, you can always ask me a little bit about them. But these cataclysmic variables are interesting since they transfer this material onto a white dwarf. Okay. Now, there's something after this stage that is called a black dwarf, and we have not been, the universe hasn't been around long enough to have time to actually form such a thing, but this is when we have no more energy source. So the star continues to cool, um, and eventually it won't have any energy left in it to have any sort of light from it. So this is where we have a color that changes from the white dwarf to red to black, or in the infrared we can see it. And after billions of years it will be dark, considered a black dwarf, and this will be the stellar remnants that are mainly um, made of carbon, oxygen, and neon. So, like I said, we have not seen these in nature, but this is the theory of what would eventually happen after billions and billions of years. Okay. Now we can talk about high mass stars. So high mass stars, we have a lot of nuclear fusion, of course. We have that in low mass stars as well. But in the high mass stars case, we can have nuclear fusion that will go even to iron. So we don't just have fusion that occurs with hydrogen and helium, but it can go as far as iron. So this is a core of a supergiant star, and we have our hydrogen, our helium, and then we get to carbon, neon, oxygen, silicon, and sulfur, and then all the way to iron in that middle part there. Okay, so this is the fusion that'll continue to happen to create these um, heavier elements. Okay, so as that builds up, as the iron builds up in the core, the energy, or there's no energy that can be gained by fusing that iron, so it just takes energy to fuse the iron. So as the mass increases, electrons um, are pushed into the nucleus and form neutrons. So this is where we now have um, degenerate neutron pressure instead of degenerate electron pressure in the star. So the degenerate neutron pressure keeps the core from collapsing. So comparing the two, we have the low mass stars that had the degenerate electrons. Now we have degenerate neutrons. And from this, we can get a neutron star. So the core from the high mass star will collapse from the size of Earth to about 20 kilometers, or about 12 miles in size. So that is going from the size of Earth to the size of, say, a small town or a city. Okay, so this is how much it collapses in size, and it is a very quick process. Okay, so this core is now called a neutron star. And material will fall into the newly formed neutron star, and that material will bounce back or rebound from the neutron star and will create a shock wave that moves throughout the star and disturbs the outer layers, which expels them into space. So we can kind of see that in each of these. Um, let's see, we've got the neutron star and then it collapses and expels this material into space. Okay. And this is called a type 2 supernova explosion or a type 2 supernova when this happens. All right, so let's look at the different fates of the stars and objects with different masses. So this table is in your textbook, and we have different initial masses. So where we're going to say the mass of the sun is equal to 1. Okay, so we have something right here. This is where the sun would be. Equals mass equals 1. The sun mass is equal to 1 here. Okay, so if we have something that is let's see, a tenth of the sun's mass, we'll have a planet. Okay. Then if we have something the tenth to it's a tenth, yeah. No, 1%. Yeah. 1% of the mass of the sun. So let me write that. 1% of mass of the sun. Now it makes it a little easier. We will have a planet, or if we have 1 to 8% of the mass of the sun, we'd have a brown dwarf that we have talked about previously. If we have something that is from 8 to 25% of the mass of the sun, we'll have a white dwarf that is mostly made of helium. And as we go on, we can see that the white dwarf will be made of different substances depending on that beginning mass. So here we have a white dwarf mostly made of carbon and oxygen, and so forth. A white dwarf made of oxygen, neon, and magnesium. Then if we have something that's 10 times, 10 to 40 times the mass of the sun, we'll get a supernova explosion that leaves a neutron star. If it's greater than 40 times the mass of the sun, then we'll have a supernova explosion that leaves behind a black hole. Okay, so I have this also here, and note that we have very few high mass stars. It's much more common to have a lower mass star. Okay, so we have lots of low mass, whoops, stars that are similar in size to the sun. It's very common, but when we get into a higher masses, they're not as common at all. Okay. All right, so let me go ahead and pause here and then we'll continue our discussion with supernova in the next video.